Welcome back. In the last lecture we had a discussion about the geometrical representation of signals. Let's do a recap. Okay, so we have m energy signals. Energy signals means the energy is finite. Energy is finite means if I have a signal Si, it implies integral 0 to t Si squared t dt is less than infinity, that is finite. Okay, so we have m energy signals and n basis function. Now I can represent my signal Si of t as a linear combination of my basis functions as Sij phi j of t. Okay, this is in the interval 0 less than or equal t less than or equal to capital T, and we have I is equal to 1, 2, etc. up to m. That is, I have m energy signals which are represented in terms of this basis functions, and each of the signal will have maximum duration of t. Okay, each of the signal has a duration of t, that is Si of t is non-zero for the interval 0 to t maximum. Okay, now how to find the coefficients Sij, that also is discussed in the last class. Sij, it is the contribution of Sit in the direction phi j of t, or you can say contribution of phi j in signal Si of t. You can say in both ways, that is, this is the contribution, Sij is the contribution of the signal Si in the basis phi j, or how much, or it is the contribution of the basis to this signal. Okay, how much phi j contribute to the signal Sij. Let's look into this equation. Si of t is this summation, so this is the contribution of each basis to this signal, and in a different angle what we see is this is the contribution that Si gives in the direction phi j. Both ways we can think. Okay, now to find Sij, what we have to do is to find Sij, find Sij we need to find the inner product. Inner product between Si of t and phi j of t. That is, Sij is equal to integral 0 to t Si of t phi j of t dt. This is Sij. Right. Now, conditions on basis functions. Orthogonality, okay, normality. Together we call it orthonormal. Okay, which means bases should be orthogonal. Okay, that is phi 1 of t, inner product between phi 1 of t, or say phi I of t and phi j of t, inner product is 0. You give any value for I and j except I is equal to j. This is for I is not equal to j. You take any two different bases, find the inner product. The inner product will be 0. That is orthogonality. And normality means energy of your basis will be unity. That is phi I of t square dt equal to 1. So together we can represent it. It's something like this. That is orthonormality. Basis should be orthonormal. Bases should be orthonormal. Means that integral 0 to t phi I of t phi j of t dt. So this is the inner product, is equal to 0 if I is not equal to j, 1 if I is equal to j. So I is not equal to j, that is this condition, inner product between two different basis functions. Okay, so that is 0. Now when I is equal to j, it is the same basis. Okay, so then this integration will become integral 0 to t phi I square t dt, which is nothing but the energy of the signal, that should be equal to 1. So these are the conditions on the basis functions. Okay, now as we have seen above, this equation, okay, this equation, let me write it here again. Sij is equal to integral 0 to t Si of t phi j of t dt. Okay, what is this? Finding the contribution of each basis to this signal, or finding the contribution of the signal in each basis. This is in a sense, it's a correlation. That is, correlation means what? How much two signals are related to each other. That's what we calculate in correlation. So this is in a sense correlation. So how much Si and phi j are related to each other, that is represented by Sij. If Si do not have any contribution in phi j, or vice versa, phi j do not have any contribution in Sij, this value will be 0. Okay, right. If si if there is a contribution, it will be non-zero, and that value represents how much it is related to each other. So this is in a sense correlation. Now we have two basic processes here, that is, first one is analysis. Okay, that is what we do here. Okay, analysis is what we find the correlation between, we find the correlation between the signal at hand and the basis function. Okay, that is analysis. That is, we find the contribution of each basis to the signal, or the contribution of the signal in the direction of basis. So that is analysis. Let me write the equation once again here. Sij is equal to integral 0 to t si of t phi j of t dt. This is the analysis equation. We have similar kind of equations in Fourier analysis, where we have analysis equation as well as synthesis equation. So this analysis process can be represented in a block diagram representation as this. So what this is the output of analysis. Okay, we give Si as input. So we have Si here, Si of t coming here, and it is going to a bank of correlators. Okay, I need to multiply it with phi 1 of t, and then integrate that, integral 0 to t dt. Okay, this entire thing is a correlator. Okay, so we have a bank of correlators. So the next correlator here, phi 2 of t 0 to t dt. Here I get S1 Si1, here I get Si2. Likewise, I have here phi n of t, and that will go to again an integrator, and I'll get here Sin. This whole thing can be represented by a vector which is called signal vector. This is signal vector. Which is equal to, so this is Si1, Si2, etc. up to Sin. Okay, so you have contribution of your signal in each of the bases. Si1 is the contribution in the first basis, this is second basis, and this is nth basis. So you collect them in a matrix form, a column matrix or column vector form. So this is a column vector, and we call that as signal vector. Now this signal vector completely characterize your signal in the basis says phi j of t, where j is equal to 1 to n. So this signal vector completely characterizes your signal in these bases. So that means if you have this signal vector, then you can construct your signal back using these bases. Now this is the analysis block. Now we have the synthesis block. Once you know the signal vector, from the signal vector you can construct your signal back. Okay, you can construct your signal back. That is called synthesis. Okay, you have the signal vector Si. Okay, Si. So you have your signal vector Si, which is nothing but your Si1, Si2, Si3, like that. So Si1, so this is your signal vector Si1, Si2, like that. So to reconstruct that, what I have to do is I need to implement this equation, that is Si of t is equal to sigma j equal to 1 to n Sij phi j of t. I need to implement this equation. So to implement this equation, what I have to do is take the first member of the signal vector, multiply it with first basis phi j of t, and take the second vector phi, so this is phi 1 of t. Okay, phi 1 of t, this is phi 2 of t, multiply with the second basis, that is Si2. Similarly, we have Sin multiply with nth basis. Okay, now add all of them together. This will give you your signal Si of t. Okay, so you have your signal vector here, signal vector. Okay, now from the signal vector you have reconstructed your signal back, and this is a block diagram representation of the synthesis process. Right. Now we have a question, that is, if I have the basis functions, that is set of phi j of t, j is equal to 1 to n, I can do all these things. I can represent my signal. I can represent my signal in those bases. Okay, how to find these bases? Now, how to find these basis functions? This is the question, and you need to properly choose these basis functions, because let me show you an example. I have two basis functions. Let this be my first basis, okay, phi 1 of t, 0 t, and this is my second basis. Okay, this is 1 and this is 1 t to t, and this is phi 2 of t, and I am asked to represent a sine wave duration 2t, okay, some amplitude a, in these bases. Okay, the question is this: represent, say this is y of t as a linear combination of phi 1 of t and phi 2 of t. Is it possible? It is possible to represent this sine wave in these bases, but the resultant representation, will that be a sine wave? Okay, will the resultant representation be a sine wave? This is the question. So how we represent a signal in terms of these bases is, we can the thing that you can do is, we can scale these bases. We can multiply it with anything. If you multiply it with some value, this function still be a square or a rectangular function within 0 to duration 0 to t. Okay, when you multiply, the only thing changes is its amplitude. Similarly here, when you multiply this with some constant, it will change the amplitude, but it will be always a rectangular function from t to 2t, and you can add them together to form a new signal. But here we have sine wave. The maximum extent to which we can represent this sine wave using these functions is this. Where you multiply phi 1, this is nothing but y cap of t. I represent this by y cap because it is not exactly y of t. Y of t is a sine wave, but we have obtained here is a square wave. Y cap of t is nothing but 8 times phi 1 of t minus 8 times phi 2 of t. What you have done is multiplied phi 1 with a, multiply this with minus a, and added them together to form the signal. And this is not sine wave. Okay, this is not sine wave. Why it is so? Because this signal does not fall in the space represented by these two basis functions. So if a signal does not fall in the space, you cannot represent that signal. For example, suppose you have take the Cartesian space. Okay, you have x, y and z. Now assume a point here. Okay, and you are asked to represent, say this point is for, let it be 3z and 2x and 2y. Okay, so this point P is equal to 2x plus 2y plus 3z. Now you are asked to represent this point in 2 dimensions. That is, you don't have the third basis z. but the point falls here, but you are restricted to use only these two bases, x and y. Can you represent this point exactly? No. By x and y you can represent only this point, okay, p dash or p cap. This is why this is what is called projection of the point P in this two-dimensional space. Okay, so you have a point which falls in three-dimensional space, but you are asked to represent that point in two-dimensional space. Then what you have to do is you have to project that point into the two-dimensional space, and that will be your estimate or your approximate representation of this point. Okay, so this is what happens here, because you cannot actually, this sine wave does not fall in this space represented by phi 1 and phi 2. So you cannot represent it exactly using these two bases. The maximum possible solution is this, a square wave. This is the maximum possible solution for this sine wave in this the space constituted by phi 1 and phi 2. Now if you want to represent a signal exactly in its bases, you may have to choose the bases carefully. If you choose these bases for this sine wave, you cannot represent that exactly. So you need to select some other bases to represent sine wave. And this is what we will discuss in Gram-Schmidt orthogonalization procedure. So let's see Gram-Schmidt orthogonalization procedure next. Before moving into the signal space, we can see that in vector space, that is, assume that you have two vectors like this. Okay, two vectors. This is vector 1 s1 and this is 2 s2, and you have two vectors now. Okay, two vectors now, and you are asked to find two basis vectors to represent these vectors. What are the conditions on the basis? They should be orthogonal as well as normal. Okay, so one thing that you can do is this. So the step 1, choose any vector as the first basis. Okay, so I am choosing phi 1 as s1. The problem here is that s1 may not be normalized. Okay, the basis should be having normal energy. So what we can do is that divide it with energy of that signal, root of the energy of that signal. So I choose the first basis as any of these signals. So here I have chosen s1 as the first basis normalized with its energy. Now what I'll do is, so this, what is phi 1 then? Phi 1 is a vector which has the same direction as s1. Okay, phi 1 is s1 itself, but the length of that vector, this vector is unity. So it is the same vector with length unity. Okay, unity. So this is phi 1. Now what will be s1? S1 is nothing but root e s1 into phi 1. You need to multiply phi 1 with the root of the energy of s1, then you will get s1. Now how can you find the second basis here? To find the second basis, what you have to do is find the contribution of this signal s2 in the direction of first basis. Okay, you might have done these things in your basic mechanical mechanics course. You have two vectors, find the projection of one vector on the other, and all those things. So what you have to do is to find the projection or the contribution of S2 in this direction, or both ways you can say the contribution of phi1 in this vector or contribution of S2 in this vector phi1. Okay, to find that, what you need to do is find the inner product between S2 and phi1. So that will be the contribution of S2 in this direction, or that will be the contribution of phi1 in this vector. Both ways we can say. Okay, now what you do is construct a new vector G2. It is nothing but S2. So these are the vectors. S1 is also a vector. S1. Okay, S2 minus, okay, S2 phi1 into phi1. So this is the length of the vector and this is the direction. Okay, so this is the length of the vector and this is the length. So total is this is the vector, that is this entire thing is this. Okay, this is this vector, or we can say this is S2 phi1 of phi1 into phi1. Okay, now what you do is you have found the contribution of phi1 to S2, or contribution of S2 in this direction of phi1, then subtract this from this vector. Okay, that's what we have done here. G2 is S2 minus contribution. Okay, now what you will get a vector. So this G2 now will not have any contribution of phi1. S2 had a contribution of phi1, which is nothing but this. So what I have done is, from S2 I have subtracted that contribution and generated a new vector G2, and this G2 will not have any contribution of phi1 because I have already subtracted that from S2. So which means that G2 and phi1 are orthogonal. They are now orthogonal. But to so orthogonal means it will be something like this. So G2 will be something like this, orthogonal, 90 degree. Okay, this is G2. Now to generate the second basis, what I have to do is phi2 is G2 divided by root of its energy, E G2. So this will give you a basis. So this may be phi2. I have normalized it with energy. So G2 phi2 is a vector which is in the same direction of G2 but with unit energy. This can be extended to any dimension. If I am going for the third dimension, if I have three signals and if I need to I need to find a third basis, what I have to do is I need to find the contribution of the third signal in the direction phi1 as well as in the direction phi2 and subtract that from that signal. That will give you the third basis function, basis vector. This is the procedure. Okay, this is exactly what we do in the signal space as well, where I have M. Okay, so this is in vector space. Now in signal space. Okay, signal space. So what I have here is M energy signals. Okay, I have M energy signals. So the first basis is found by arbitrarily choosing any of the signal. Here I have chosen S1 of t. Okay, divide by its energy E1, where E1 is integral 0 to t s1 square t dt. Okay, now s1 of t is equal to root e1 phi 1 of t. Okay, now to find the second basis, what I have to do is I need to find, okay, this is the step 1. Okay, now step 2, to find the second basis, what I have to do is I need to find the contribution of my second signal in the first basis, so in the first direction. So that is nothing but inner product between my signal and the basis, the first basis. Okay, so I am finding the contribution or contribution of my signal in the first basis direction. So this is S21. Now I construct a new signal G2 of t, that is equal to S2 of t minus S21 phi 1 of t. So this will give you a signal G2 of t, which is, okay, G2 of t is orthogonal to phi 1 of t, because G2 of t is constructed from the signal S2 of t by subtracting the contribution the first basis has in that signal. Okay, the contribution of first basis signal is in S2 of t is subtracted from S2 of t. Now G2 of that is G2 of t. Now G2 of t does not have any contribution of phi 1, so they are orthogonal. Now to find the actual basis function phi 2 of t, I just need to normalize this G2 of t divided by energy of that EG2 of t. Okay, or EG2, let me call it by EG2. So this is the second basis. Now to find the third basis, again I need to find contribution of the third signal in the first basis and second basis, subtract that from the third signal, and that will give you the third basis. Okay, so this actually I can substitute these things here. So phi 2 of t is S2 of t minus S21 phi 1 of t divided by, and root E2. EG2 is integral 0 to t G2 of t, G2 square t dt. So you can actually work it out, and it is there in my note, and this results in E2 minus S21 square. Substitute these things here, do x plus y, the x minus y the whole square, just use that equation, and then you'll get this thing. So substitute it here. So this is E2 minus S21 square, root of that. Okay, this is phi 2 of t, and actually we can generalize this. Okay, generalize to any dimensions. We have here we have two signals, two bases. You can have n number of bases, so phi 1, phi 2, phi 3, phi 4, etc. So we generalize like this. You can define Gi of t like this: Si of t minus sigma j equal to 1 to I minus 1 Sij phi j of t. So what is this? So you are constructing the ith generator function. Okay, let me call it as generator function. to construct the ith generated function, what you have to do is you have to subtract the contribution of the signal Si in all the other directions up to I minus 1. For example, if you are finding the third generator function, you need to find the contribution of Si in first basis as well as second basis and subtract it from Si. If you are going for the fourth, you need to find the contribution of S4 in phi 1, phi 2 and phi 3. Subtract it. Sij is nothing but integral 0 to t Si of t phi j of t. Now given gi of t, we can find phi j of t as, or phi I of t as gi of t. Simply normalize that function divided by root of integral 0 to t gi of t square dt. This will give you the basis. Okay, so you can use this equation for any dimension. So this is Gram-Schmidt orthogonalization procedure. Okay, now let us see an example of this, and I have given you solution for the question paper, previous question papers. In that I have worked out all these examples, and 2-3 examples are there. This is taken from your textbook. Okay, 7 hacking digital communication. So the problem 5.3. Okay, so you have 4 signals S1, S2, S3, S4. 0 to t by 3, 0 to 2t by 3, t by 3 to t, and 0 to t. And you are asked to find a set of bases for these functions. Okay, so the first step. Okay, this is a solution for the problem. Okay, so the first step is simply select the first signal itself as the first basis by normalizing that. So we need to find the energy of that signal. So integral 0 to t Si square t dt. So this signal is only up to t by 3. So that this integration will become 0 to t by 3, and in that case the signal is 1. So 1 square t. So you will get t by 3. Okay. Now the first basis is this. You just need to divide the first signal by root of this. So what you will get is this. You just need to so phi 1 of t, you need to divide this signal by root t by 3. Root t by 3. So this will become 1 divided by root t by 3. Then root 3 by t. That will be the amplitude of the signal. Okay, and it will be extending from 0 to t by 3. Okay, right, that's what we have written here. 0 to t by 3, root 3 by 2, 3 by t, and 0 otherwise. Now the second basis function. To find the second basis function, what you have to do is you need to find S21. Okay, S21. What is S21? Integral 0 to t S2 of t phi 1 of t dt. Now see, the second function extend from 0 to 2t by 3, whereas the basis extend only from 0 to t by 3. So this integral, you take the value t by 3 for this integral, which is the minimum. Okay, so this will become integral 0 to t by 3, because this product is 0 afterwards. 0 to t by 3. So okay, S21 in this interval is 1, and so 1 multiplied by phi 1. Phi 1 is root 3 by t in this interval dt. This is equal to root 3 by t integral 0 to t by 3 dt is equal to root 3 by t into t by 3. Okay, this is root t by 3. Okay, this is S21. So to find the second basis, you just need to do this operation S21, S2. So S2, from this you need to subtract. Okay, from this is S2, S2. From this you need to subtract what? H21 phi1 of t. S21 is root t by 3. Phi1 of t is this. So you have a function up to t by 3 and it is having value root t by 3 into, okay, into root 3 by t. So both of them cancels together, so you will have 1 here. Okay, this is 1. Okay, 1. So the resultant signal is, okay, you subtracted this from this, so you will have a function. So it is, this signal is 1 from t 0 to t by 3. This signal is 1 from 0 to 2t by 3. Then when you subtract this from this, you will have a signal which is 1 from t by 3 to 2t by 3. Okay, okay, so this is that signal. So this is this one. Okay, now you need to normalize it with energy, and you get this. You can do it yourself and you get this thing. Phi 2 of t is root 3 by t from this, from t by 3 to 2t by 3. Alright, okay, now to find third signal, again you need to find the contribution of first basis, this S31, contribution of first basis in the third signal, which is 0, because contribution of first basis is extending from 0 to t by 3. Okay, 0 to t by 3, but the third signal starts from t by 3 to t, so they don't have anything in common. That means this does not have any contribution to this third signal, so that's why you have 0 here. Okay, you have 0 here. Now the second S32, that is contribution of second basis to the signal S3. There you will have something, because the second basis starts from t by 3 and end in 2t by 3, and you can find that I have given you all the required documents, so you can just see those and find, or you can find work it out yourself. You will get this one, and again you can actually use the equations. Okay, gi of t, and use put I is equal to 3, then you will get this equation, and simply calculate g3 of t, and you will get then find the energy of g3 of t, normalize that, and you will get phi 3 of t as this is phi 3 of t, phi 3 of t. Okay, now again we have 4 signals, so naturally you may think that we need to go for the fourth basis, phi 4 of t, but that is not required, because you can actually represent S4 by these bases itself, because this is from 0 to t by 3, this is from t by 3 to 2t by 3, and this is from 2t by 3 to t. If we simply add them together, you will get a function which is extended from 0 to t, which is having an amplitude root 3 by 2. Now what you have to do is, here S4 has an amplitude 1. So to make this amplitude 1, you just need to multiply it with, multiply with root t by 3. So which means that S4 of t is equal to phi 1 plus phi 2 plus phi 3 multiplied by root t by 3. Okay, so you don't need a fourth basis. The fourth signal can actually be represented in the other 3 bases itself. Okay, this is the example, and you have different examples given to you, work it out multiple times. That will give you an insight to the problem, and if you will be able to do a different problem if it is given in the examination. Okay, so with this we wind up the second lecture. Thank you.